All right, in this SageMath interlude, we are going to go over how to define polynomial rings and how to do matrix arithmetic in Sage. So let's start with polynomial rings. There's a lot of different ways of doing it. We're going to go hardest to easiest. So we have to give our rings a name. I'm going to say that our polynomial ring's name is R. Great. And then we can do a variety of things. We can ask it, we can first of all tell it what our variable is going to be. Let's use, I don't know, a capital lowercase x. So r dot lowercase x. And what we want that to be is a polynomial ring over, let's say the integers first. Okay. Now this won't do anything when we evaluate it. It's just going to return blank. But if we ask it what is R, it's going to say it's a polynomial ring in one variable. That variable is x, and it's over the integer ring. Great. Now what we can do is we can use x as a variable and define some polynomials. So let's define 2x cubed plus x squared, I don't know, minus 1. And let's look at what it gives us. All right, it tells us that f looks like that. And let's define another polynomial. These polynomials have no meaning, but say negative 5x to the 5th plus 4x to the 4th minus 3 times x cubed plus 2x squared minus 1x or minus x. And let's say that's our g. All right. So what we can do is we can do polynomial arithmetic. So we can look at f plus g, and you can verify that that's the right answer. You can look at f minus g, and you can verify that that is also the right answer. We can look at g minus f. So we should get the negative of that, and we do. Great. We can also do polynomial multiplication. So there's f times g, and we know that polynomial multiplication is commutative. So if we look at g times f, we should get the same thing, and we do. We can also, as sort of a prelude to what comes next, we can ask if the polynomials f and g share anything in common. They don't. They don't have anything in common whatsoever. But notice if we were to modify our polynomials, say maybe I took g and I multiplied it by f, then my GCD of f and g should now be f, right? Because g doesn't have anything in common with this part, but it has a full-on f in common with this new factor. So we should get f back from that. And we do. Great. So that's how you might define the polynomial ring over the integers. But what if we had a different guy? What if it was like z mod 5? Let's get rid of this part. So remember to say z mod 5, we do gf and then whatever prime we're looking at. And let's actually have it print f, g, and then the GCD of f and g. And we're going to watch what happens. So, print f. Let me just, instead of trying to format on the fly, let me just have them print on separate lines. All right, so what should we get? Well, we should get the reduction mod 5. So this is all fine, and the -1 should become a 4. It does. Great. And then this x to the 5th term should go away entirely. It does. And this should be 4x to the 4. -3 is congruent to 2 mod 5, so plus 2x cubed plus 2x squared, and then -1 is congruent to 4. That's exactly what we get here. And they still don't have anything in common. Great. So you can do arbitrary rings here or fields. We could have put, so GF5 of course is a field. We proved that. We could put, if we want, the rationals here as well. And then we could add some rational expressions. So we could have like, I don't know, -1/2 x, maybe this is 5/24, and so on. And we can still do our polynomial arithmetic. So I won't drone on about that. But this is how we can define a polynomial ring and then manipulate polynomials. There are other ways to find a polynomial ring, so I'll talk about those as well. I have a preference for this way because it tells me what my ring is and then what the variable is, and the syntax sort of shows up again and again in Sage. So I like to have like a fallback syntax that I know is usually what's Sage is expecting. But there are other ways, and you might like the other ways more. So with that in mind, here's another way. We can tell it what the variable is going to be inside of the argument to polynomial. If we evaluate, nothing should change. We got some more interesting factoring here, but nothing should change. It's a little bit curious why it chose to factor it here and it didn't factor it before, and I'll need to investigate that. I'm not sure why it did that. So that's another way of doing it. Even simpler, what we can do is we could say, hey, I want to look, this will match the notation from algebra. Hey, I want to look at QQ adjoint X. That's our polynomial ring with coefficients in Q. And that will also return a similar gadget. And we could have done, I don't know, CC here instead. CC for complex numbers. These are all complex numbers. Every rational number is a complex number, and we get a similar thing. So this is polynomial rings. I also want to show you some matrix arithmetic. So how would you define a matrix? I think we've already looked at them, but I want to remind you of it. So suppose I wanted a matrix in GF5. I just have to say GF5, and then we're going to do a 2 by 2 matrix. So I'm going to say 1, 0, I don't know, -3, 4. Now the -3 is going to become a 2 if we look at this. That's fine, because in GF5, -3 and 2 are the same. Let's now define another matrix, and instead of writing this again, I'm just going to copy. And let's make it, I don't know, 0, 3, 1, 7. Okay. And now B is going to reduce the 7. That's fine. But I want it to be this in case we decide to change this to a different number. And let's also define C. C is going to be in the same guy, and then I don't know, maybe it's 1, 1, 1, 1. All right. Now, one of the things that we looked at in class was, it was on our group worksheet. We didn't have time for it, but we wanted to understand whether or not matrix multiplication was associative. So we can even just ask Sage, hey, Sage, let's compute A times B times C, and let's print it out, say. Or actually, let's be even clearer with computing B times C first. So I'm going to say BC is this product, and I want it to print A times BC. And then I'm going to say AB is this product, and then I want it to print AB times C. Okay. And if matrix multiplication is associative, which it is, we should get the same answer. All right, so we get 3, 3, 3, 3 for the first guy. It's kind of odd. And then 3, 3, 3, 3 for the second guy. Great. So this is an example checking associativity, but we can experimentally verify it with some random matrices here. Let's also look at the distributive property. So I'm going to write BPC for B plus C. So that is what we want to do is we're going to check A times B, B plus C is A times B plus A times C. Okay, so that's what we're checking with this example. This isn't a proof, it's just a check. So I want B plus C, and then I want to multiply A with B plus C. And then we have our AB, we also need AC, so that's going to be A times C. And then I want here to print out AB plus AC. Now, if it's associative, or sorry, if the matrix multiplication and addition satisfy the distributive property, this should return the same matrices, and they do. Great. So anyways, this is just some more work on matrices and how you can, if you wanted to, experimentally verify some of the properties. But again, this is not a proof. Okay, so in this video, we looked at how you can manipulate polynomial rings and how you can look at matrices and the matrix arithmetic within Sage.